Hi everyone, my name is Gino. Today I'm going to talk about interactive navigation in real world. So in my research group, we are working on developing robotics technologies for human-robot team, in particular in challenging environments and difficult conditions. And social navigation, where the robot is supposed to navigate in dense human crowds, and also in the creative AI space where we use robotics technologies to enhance human creativity. So the ultimate goal here is to develop robot navigation algorithms that will work in a real human environment, such as this one. So as you can see, this is a very challenging problem. And there are lots of static obstacles you can see, such as buildings, poles, and so on. And also there are dynamic obstacles that are moving, including pedestrians, bikers, and cyclists. And some of these dynamic obstacles are interactive, so we can engage in a conversation or negotiation. And if we spend a little bit of more time on this video, we also realize that there are invisible rules that human defined, including traffic rules and social norms. So let's formulate the problem of navigation. So from the robotics perspective, this is a problem where given a goal, to find the sequence of actions to move from an initial state or the current state to reach the goal while minimizing the overall cost with respect to some objectives. The objectives include mostly focusing on goal-oriented efficiency, such as finding the fastest path or the shortest. And another also important objective is ensuring safety. So try to avoid the collision and also avoid the difficult terrain. So what is interactive navigation? So as I mentioned, maybe some of the agents in the same environment can specify the robot's goal using natural language, or robot can engage in a dialogue or a conversation with the other agents in the same environment to learn more about the context and the tasks. So we can see it as a natural communication wrapper around this autonomous navigation problem known as Go2XY. And most of these recent approaches are seeking end-to-end approaches to solve this problem, whereas more traditional approaches were modularized. So in this talk, I'm going to go over some of the end-to-end approaches and also modularize the approaches where we can take advantage of existing tools. So the first part of the talk will be the communication coming from the robot to the human commander. So image captioning is a subproblem in this category, so that robot can take this imagery input and then generate a language description to communicate with the human user, maybe through a low bandwidth network. So let's use this example to generate a caption. So using one of the holistic image captioning tool, what we get is a man standing on the street. So I'm going to ignore the latter part because the recurrent neural nets tend to generate noisy outputs towards the end. And this description is general, but it is correct. Man is standing on the street, but it's not really detailed enough to be used for maybe a higher level task, such as finding this person given this description. So this description, man standing on the street, can apply to many of these people on the street. So it is hard to identify the target person. So what we are aiming to get is something like this: a short-haired man in red shirts. So that's giving enough descriptive information so that other people or other agents can identify the target person. So the research questions here are, how can we generate these detailed captions? And then the second question is a little bit more difficult to answer because a lot of existing evaluation methods are using some small number of human-generated captions as if they are ground truth. And some of the metrics even penalize these longer sentences, which we aim to generate. So some of the existing approaches we'll go over. So the sequential models are the earliest approaches where we use the CNNs to encode the imagery input and then use some more like a recurrent neural net such as LSTM to decode that same information into the language. So the advantages of sequential model are it tends to generate grammatically correct sentences, but the semantic part is relatively dark. On the other hand, compositional models use a recursive joining of the more phrases into longer phrases. So semantically, these sentences generated by the compositional models are richer, but the fluency is a little bit lacking. And then there are a few more existing approaches that are trying to utilize the semantic information, such as this bottom-up attention model, where they replace this grid-like structure to extract the CNN features. Instead of doing that, they take advantages of existing object detectors. So they use bounding boxes instead of these random grids. So this improved a lot of overall performance. And then another approach is why not use attributes? So we can detect attributes and make use of them. So the proposed approach is compositional neural module network. So the what we are aiming here is to get the best from the both sides. So achieving the semantic richness while also keeping the fluency. So this is a work mainly done by Junja Tian. He's a PhD student at Georgia Tech. And then showing some of the results. So quantitatively, as I mentioned, the evaluation metrics are comparing the results with the existing human-generated captions. And our approach outperforms the baseline on both fluency and semantic richness metrics. And we also did the human evaluation because of the limitations of the existing metrics. So here, quickly, we can see the blue are the proposed approach, whereas the orange is the baseline. We do better in terms of the semantic categories, such as color, counting, and spatial relationships. So some of the sample results here. So we can see our approach generates more specific description. So in this example, the baseline generates a group of children, kind of choosing the general term to be safer. But our approach is boldly choosing a specific number, 3 children. So and also in this next example, baseline chooses a piece of fruit. It can be applied to many different fruits, whereas our approach says red apple. So by doing this, we are taking the risk of getting more penalty, because if it's wrong, then the evaluator will say, oh, this is incorrect. So, but because our purpose was giving more specific description, we still wanted to do it, and based on the general metrics, ours is still comparable with other state-of-the-art. Okay, so that was the part of communication from robot to human. And then now we want to also look at the other side, which is understanding the natural language command. So here we also want to see some ideas that can take advantages of existing tools. And so revisiting the go to XY problem. So in this plain go to XY problem setting, the goals and initial states are given in an XY coordinates, and the hard constraints in an earlier work is binary obstacle or not obstacle. So the binary obstacle map, and the algorithm is trying to avoid a collision with obstacles. And the secondary thing is a so-called soft constraint. So this is okay to violate, but our preference is using a different route. So an example is a surface type. So if it's a gravel, maybe it is harder to for the robot to navigate. And so the path chosen would prefer smoother surface. So how does the robot do this type of things? So the robot uses sensors to perceive the environment to avoid these difficult obstacles, or to try to avoid challenging terrain. And the overall objective is to optimize the travel cost. And now moving to the interactive navigation, these soft constraints or hard constraints can be specified using natural language, and then also the goal. So the vision language navigation problems usually take it as an end-to-end problem where the inputs are the language command and the visual inputs, and then the final output is action. And here we will revisit the somewhat older approaches where view this problem as a translation problem. So take the natural language command and then translate that into some go to XY command so that we can leverage existing robotics tools. So the advantage of doing this is we can make use of existing planning tools and grounding tools, and also perception modules that can recognize different types of objects. And then also we can include prior knowledge when available, and also combine these different information from multiple sources in a more principled way. So using a simple example of navigate to the building behind the car. So robot starts using its sensors to try to perceive the environment, and then try to find the landmark that's matching the command. So here we already see some problems. So there's a huge difference between computer vision and robotics vision. So in robotics, visions provide somewhat low-level input to the high-level decision-making, such as planning or some task-related decision-making. So if the error is large in the perception level, then it's very hard to expect good performance at the task level. So for instance, here, if another vehicle is detected as a false positive, then it already creates ambiguity. Which car do you mean behind which car? So how do we resolve such ambiguity? So the idea is to ask questions. So we can communicate back to the user and to clarify which vehicle the user meant. And then the third part is the unseen part of the environment. So if the robot is navigating in a complete unknown environment without any prior information, then it's even hard to know what the target is within the field of view or not. So how to resolve these issues? So in this case, the building is not within the field of view of the robot. So, but to a human, this is not a difficult problem because the command said that the building is behind the car, so we can imagine the space. So that's one of the ideas that was used in this approach. So again, using another example, so this is, suppose you are the robot looking at this scene and you've never been here before, and then the command is navigate left of the building to the traffic barrier that is behind the building. So to a human, it is a very simple command. So I asked this question to many people, and the majority of the people come up with a very similar plan. So the majority, I mean, 75 to 80%. And then there are some 20% of people who come up with a completely different plan. But this kind of shows like innate ambiguity that's contained in language. And also, what's interesting is even without that first frontal view of the camera image, we can just give this natural language command and people will come up with the same very similar plan anyway. So how do we do it? Because language can provide a already pretty good visual information in using description. So the idea of assumptive planning is exactly that. So how do we generate this, hypothesize this environment and the task just following the command. So navigate to the traffic barrier that is behind the building. But the only thing that we are seeing is a wall, like the frontal wall. But we can imagine the building because we've seen similar buildings before. And then we can imagine the space if we know spatial concepts, like what it means to be behind of something. And then we can kind of set the target location of the goal, which is the traffic barrel. And then start planning using a hypothesized goal. And it doesn't matter how accurate the location of the hypothesized goal is, as long as it's giving the right direction to get more information about the real world. So later we will see an example video. And here, the one part of the language grounding is how to determine which object or the landmark is the one that was referred in the command. So I'm not going to go into the detail of the algorithm, but we use the probabilistic approaches. And the really important part here is knowing what's in the field of view and what is not. And being a probabilistic approach, sometimes it's hard to model the space that's unseen. So including the space, the possibility of the target not being within the field of view was an important key idea here. Okay, and then the second part is training the robot for general concepts such as spatial constraints. So we use the imitation learning idea here. So quickly, the idea is this is one of the navigation mode, so Matsuku. So unless you understand Japanese, you have no idea, and I'm going to show you a demonstration. So you're getting slowly getting the idea what Matsuku navigation mode might be. And then there's another Shinsukani mode, and then I show another demonstration. So we can see the two different navigation modes, both going to the same destination, but in a different way. So we train these concepts so that the robot can generate the type of cost map that will induce such a behavior. So in this heat map, for instance, blue is a low cost. So in this Hizukani mode, it will prefer going near the buildings. Okay. So we used to use feature engineering, which was a painful process to design the features, which was also the secret behind the success. And now we use a deep learning version of that so that we don't have to domain engineer the features. So the network learns useful features to generate good cost maps. Okay. So to explain results here. So the test environment was a large simulated town, and also some of the real the locations that we use. And as you can see, this includes all 4 seasons with the different background colors, different lighting conditions, and different temperature. And also the evaluators are very subjective, the human evaluators. So this kind of illustrates the robotics challenges. And then this one is showing the video of that example we looked. So as you can see, the robot kind of imagines the space and then creates this hypothesized goal. By the way, this video was created completely from what the robot sees and how the robot interprets the world. So you can see while the robot is moving, it keeps updating the hypothesized goal. And when it's confirmed in the real space, if it's not there, it updates to a new location so that it can search the space until it actually detects the real goal. So, okay. So a little bit of a quantitative result. So being a robot experiments, the numbers are pretty low because it's very time consuming and difficult, expensive. And compared to an earlier approach without the assumptive planning idea, the task level performance was like around 50%. So given the navigation command, the robot can reach the goal around 50% of time. By the way, the current state-of-the-art performance on the visual language navigation is a little better than 50%. So it is not a really bad performance, but still it was considered a failure. So after we added this idea of assumptive planning and improved the perception, improved the language grounding, we were able to reach like 70, 80, 90% task performance, which was a substantial improvement. So the proposal here is these ideas may be combined with these end-to-end approaches that people are trying to use. And as navigation tasks and directions become complex and more and more complex, learning and having this general knowledge of about the semantic meanings and the spatial concepts will definitely add benefits to these approaches. And then as another thing to mention is that the real world experiments are very time consuming, expensive, and the evaluations are subjective. So that leads to the future directions on interactive navigation. So there was a recent paper by Peter Corke and his colleague about what we can learn from the computer vision community. So in computer vision, what we have done really well is having this evaluation paradigm almost. So having the data sets and creating challenges so that many people can participate and make huge improvement. So it has been very successful, and it's actually hard to have a analogous evaluation platform for robotics because everyone uses different robots and everyone tests on different environments and so on. So how do we create something that's still measurable but comparable with the other approaches? So we need more data sets, and we also want to use the simulation platforms. So there has been a great improvements on the simulation technologies as well. So the imageries are very high fidelity, and also there's lots of reinforcement learning platforms and so on. So one wish list here is a lot of these synthesized examples assume almost a perfect vision, but we actually need the other end. So how do we take advantage of language or other inputs when vision is not performing very well? So um, so if it can be configurable so that the approach can be prepared uh, in the range of difficulties, vision difficulties. So if there's no vision, can you still rely on natural language input? And also if there's a perfect vision, well, the problem is much more easier. And another thing is we are currently so far have discussed mostly stateless command and control, and we want to use this communication pipeline to engage in a dialogue or conversation so that the robot and the human commander or the user can share information back and forth. And finally, the meta reasoning part is there is a planning decision maker, but this meta reasoner is the one that's checking whether the planner is actually making the right decision. So it keeps asking, am I going the right direction? And this is also related to this anomaly detection or where the idea is when the vehicle is hijacked by a third party. So if it's behaving not the way it's supposed to, then this meta reasoner should be able to detect something is going wrong. Okay. So thank you so much for your attention. And these are my collaborators. And then some references. Thank you.